Hello folks, my name is Gavin. I'm going to talk today about economics and capital exchange agent-based models. I have three goals for this presentation. The first is that you understand what a capital exchange model is. The second is that you understand that the dynamics of modern digitized money are complex and rich, and that the analogy between the dynamics of energy and money is profound, insightful, and perplexing. Third, I want you to get excited about exploring the research possibilities in capital exchange models. So I have a 12-minute plan here. I'm going to start with easy material. I'm going to move on to more difficult material. Then I'm going to assume that you will watch this video several times to connect the dots if you are interested. What is a capital exchange model? It's a very peculiar kind of economic model. Only the money, no goods or services, no prices for physical quantities. Just the banker's view, not the businessman's view, not the economist's view. Now something strange happened in 1971. Money became digitized. Richard Nixon, the President of the United States, decided to abandon the gold standard, so money became, shall we say, disembodied. About the same time, banks started using electronic funds transfer, so money transferred from bank to bank electronically across wires. At that time, money was traveling around the world in a very similar fashion to the way energy travels through an ecosystem. The first capital exchange models appeared about 12 to 13 years after that event, and they've been with us ever since. Now, if you're interested in the history of capital exchange models, this paper published in 2010 is pretty good. I'm not going to go through the details of it with you, but if you're interested, please look it up on the internet. Now I'm going to start by introducing the BDY models. These are coded as models A through H in a program that I call EI Lab. These are left bounded with an infinite number of bins allowed. Let's look at model A. We start with 10,000 identical agents, each given $1,000 for a total of $10 million in this little economy. Time progresses in discrete ticks. During each tick, all agents are selected randomly to form 5,000 pairs. Within each pair, a loser is randomly selected. If the loser has $10, he or she pays it to the winner. If not, he or she doesn't have to do anything. You do that tick after tick after tick until you get to some kind of equilibrium state. That's where it visually does not look any different from one tick to the next. Now I'm going to be showing you a number of screen grabs. They are probability distributions of net worth. You see, net worth is across the bottom from 0 to 2,000, and probability is up the side from 0 to 1. We see that at tick number 0, the probability that an agent has $1,000 is 1, because that's what I give him to start with. At 500 ticks, we start to see a Gaussian distribution forming a bell curve. This is the sum of many random walks. At 1,000 ticks, 2,000 ticks, by 3,000 ticks, we start to see something strange happening at the left-hand side. Remember, agents are not allowed to have less than $0. 4,000 ticks, 5,000 ticks, 6,000. 10,000, we're almost at equilibrium. By 15,000 ticks, we are well and truly at equilibrium. No agent can have less than $0, but one agent may have it all. You see that at least one agent here has more than $5,000. The average amount is $1,000, but quite a few agents have almost nothing or nothing. This is a circumstance that has afflicted civilization for about 6,500 years. The earliest instance that I've seen is on the banks of the Nile in ancient Egypt, when an official was complaining that some people have it all when most people are poor. Now, in case you think that this is a totally unrealistic model, look at the results that Drăgulescu and Yakovenko found when they looked at real-world data. The bars here represent the data that they actually got from the income tax, and the curve is the predicted shape of the curve from the BDY models. You'll notice that in the center part, it is very, very accurate. It varies a bit at the head and the tail, but in the center part, it's very accurate. Now I want to show you a variation on the BDY models. Model I, it's doubly bounded and a finite number of bins are allowed in place of infinite bins. Okay, I'm going to quickly switch over to show you an example of this. Where is my example of it? So we've got a model run that I'm calling H4820. I'll explain that a little bit later, and we're going to start it running. You notice we've got a $1 bin, a $2 bin, a $3 bin, a $4 bin. The money just sloshes back and forth between the different bins of the model as it moves from agent to agent. So number of bins, K, is 4. Number of agents, A, is 8. Wealth endowment, the amount of money that I put in at the beginning, is $20, and that doesn't change. This is a doubly bounded. No agent can have less than $1, and no agent can have more than $4. Now let's look at the code for this. This is the a minimal code. I've removed most of the commentary, so we just have the active commands here. You'll see that the working part of this code is quite simple. In this version, I choose a winner. I let the winner choose a loser. I test. If the gold of the loser is more than 1 and the gold of the winner is less than K, then the loser gives the winner $1. Now I want you to notice that this is bounded on the left, bounded on the right, so I call it doubly bounded. You've seen so far that K is the number of bins in the histogram, 4. A is the number of agents. I'm going to add a few more variables. AI. This is the number of agents in each of the bins, and capital A then is the sum of all the AI. Now I'm going to define entropy for economic agent-based models. This is inspired by the work of Dr. Victor Yakovenko. You can see his URL down at the bottom of the screen here. The entropy S of histogram H is the logarithm base K of the multiplicity of the histogram H. So that's the logarithm base K of A factorial divided by the product of AI factorial. That's the multinomial coefficient. Now, when I am putting $20 into a model, there are only a limited number of ways that you can spread it around 8 agents in 4 bins and still have $20. In fact, there are 13 ways to do it, and here are the 13 histograms. I've calculated the entropic index for those histograms. Notice, please, that the entropic index breaks the 13 histograms into 7 sets. If we plot that with entropic index versus the wealth, we get 7 spots on the graph. But this is a 3-dimensional graph because many of those spots are lying one on top of each other. I'm going to add some terminology. HKA is the set of all histograms with K bins and A agents. Notice no mention of wealth here. Well, there are a variety of amounts of wealth that you can put into a model of 4 bins and 8 agents. So HKA is all possibilities. HKAW is a subset of histograms with K bins, A agents, and wealth of exactly W. So HKAW is smaller than HKA, is a subset of HKA. Let's look at what that means. So here we've got for H48, all 165 histograms plotted here, entropic index versus monetary endowment. Here we have the different kinds of runs, a selection of them that we can have, and the number of histograms associated with each. So you see for 4, 8, 20, 13 possible histograms, 7 spots on the graph. If we put all of the agents in the $1 bin, we have $8. $2 bin, $3 bin, $4 bin. Now, here we have 8 agents. Suppose we take 4 bins and put 100 agents in. What is different? Well, now we have 176,851 different possible histograms. We can calculate the entropic index of each one of those and plot it against the monetary endowment, and you'll see that it is in fact very similar shape. It is also a three-dimensional plot. Many of the 176,000 histograms have exactly the same entropy, so they land on top of one another. So I've put this into Excel in a way that I can give you a three-dimensional plot. I just want to show you first that it is in fact the same structure, and now we'll rotate it slightly. I think this is fantastic. Note how the density of the microstates increases exponentially as you go from zero entropy up to maximum entropy. Now, this is a diagram that was first published by Josiah Willard Gibbs in 1873. When he sent it to James Clerk Maxwell, they started development of thermodynamics. Now, I can use the magic of PowerPoint to copy the main elements of that graph, extract them, stick them onto my phase space of model I, and we get a remarkably good fit. Or we could look at Crooks fluctuation theorem. You see down at the bottom of the screen here the references to Crooks' paper and England's paper. Crooks fluctuation theorem relates macro changes of state to changes in entropy. Like that. Jeremy England used it to make a bridge from statistical mechanics to evolutionary theory. So ultimately that forms a bridge from statistical mechanics to ecology to economics. And here we see, with my data drawn from model I, a replication of Crooks fluctuation theorem. Thank you for listening. I hope you take an interest in capital exchange models.